Hello everybody, this is lesson 3.5. The title of the lesson, How Reliable is Your Commute? Let's start with the specific objectives. Students will understand that the standard deviation is used to describe the spread of the data. Each observation affects the value of standard deviation. Students will be able to compute the standard deviation and interpret the meaning of the standard deviation. So as you can see here, we are covering another measure in statistics. It's called the standard deviation, and it is something that describes the spread of the data, how spread apart it is. So we'll define what it is, we'll learn how to compute it and use it in different situations. So let's begin with problem situation number 1. Should I bike? Melissa has a job in downtown Manhattan. She lives in Sunset Park, Brooklyn, and she usually takes a subway to work and back home. Recently, she learned about free bicycle parking racks just outside the building where she works. She's considering commuting by bike because subway issues have made her late to work twice, and her manager has been rumored to have fired several predecessors at her job for lateness. She decided to compare her morning commute by subway to biking. She works 4 days a week, starting at 9 a.m. each day. She timed her commute for 3 weeks taking a subway and 3 weeks biking. Table 1 gives us the data that she collected. Okay, so these are her work day commute times by bike and by subway, listed in this table. So she was able also to calculate the summary statistic. That's something that we looked through last couple of lessons. So mean, remember the 5 number summary? So we have the mean, we have the, the 5 number summary does not include the mean. The 5 number summary includes the minimum value, the Q1, the median, the Q3, and the maximum. All right, and remember we use the 5 number summary to create something that's called a box plot. All right, and that's where you see the box plot in figure number 1. Bike is on the left, subway is on the right. So looking at those two, let's go ahead and answer the first question. Looking at the summary statistics and the box plots, would you recommend Melissa bike to work on a regular basis? Explain your reasoning using the data displayed. So would you recommend her biking? I'll give you a moment. So take a look at this. All right, so let's review. Well, biking, as you could see, is less spread out. Okay, so we can definitely write that. So biking is less, or commute. Let's write it like this. Commute by bike is less spread out when it comes to time, and therefore we can say that it is more consistent. Would you agree? The word consistency, that it is within the range, like it's not spread out as much. Okay, so would you recommend her biking? Sure. Well, maybe some of you also said, but how about the weather, right? Can weather be influenced? Yeah, of course, it's a variable, but it's not raining every day, and even if it is raining, you still can bike, right? And snowing might be a bigger problem, but again, that's not something that happens on a regular basis. So if we look at the commuting overall, then on a good day, biking seems to be more reliable. Don't you agree? Alrighty, so now let's go dig more into the this idea of describing the spread. So let's look at this data deeper. So Melissa notices that her subway commute was more spread out, which we already mentioned. The spread of the data can be measured using the range and the interquartile range, IQR, which we have seen in the previous lessons. Range is simply the difference between the maximum and minimum values, and IQR is the difference between the third quartile and the first quartile. And remember that IQR represents the middle 50% of the data values, It's that rectangle that you see in the box plot. You see, so this is our IQR range, while this is the total range. Well, this one is IQR. Remember? So that's from the previous lessons. So go ahead, and what is it asking us? Let's compute the range in IQR for both the subway and the bike. Okay? I'll give you a moment. All right, so for bike, let's go ahead and calculate the range and also IQR. So the range is simply you take the highest value and you subtract the lowest, highest minus the lowest. So here's the minimum, here's the maximum. If you subtract them, you just get 6. So 6 minutes range of her commute between the lowest and the highest. And the IQR, which represents the middle 50% of all the commute times, and that would be difference between Q1 and Q3. That's your IQR, and that's only 2.5 minutes. All right, while for subway, for the train, the range is huge. Look at this, and I think it has happened to you as well, right? On a good day, you can get there very quickly, but when there are delays, it could take forever. So here, the difference between the minimum and the maximum values is 57 minus 34. That gives us 23 minutes. Look at that, 23-minute difference between the largest number and the smallest number, while the IQR, which represents the bulk of her commute, the middle 50% of her commute on a subway, is a little bit better, but still there is a 10 minutes difference. All right, so it's 10 minutes. So you understand, you just subtract those two numbers, and then if you compare this, you could clearly see the spread out for subway is so much more than the spread out for the bike. Again, giving us more proof that biking is more consistent. Alrighty, now let's go into more calculation. So the range and IQR give us some understanding of the spread, but it's not complete understanding. It's not a complete picture. In this lesson, we'll develop a measure of variability as it relates to the average, or arithmetic mean. Recall, the mean is the arithmetic average of all the data values. We'll compute it by adding all the values and divide the sum by the number of values in the given data set. So this already has been done. I'm sure you know how to calculate average. So here are the numbers. So for the bike, an average commute time is 44 minutes. We'll label it as X bar, while for the subway, the average commute is 43 minutes. Notice that the average commute time are very equal, very similar, right? So on average, it looks like it takes about the same time to get to work on the subway versus the bike. It's almost the same. However, you see the average does not give us the full picture. So let's see. We're going to calculate how far, and listen to this carefully, we're going to calculate how far each data value is away from the mean. This is called a deviation from the mean, and this is what we're going to be denoting this as. Well, let me actually be consistent with my highlighting. So I'll highlight the subway. Well, it doesn't matter, but let me, just to be consistent with this 44, I'll highlight bike with the yellow highlighter, and then we're going to start computing it. And this x minus x bar simply means the deviation from the average. Okay, so the x bar is the average, and we're going to calculate that deviation. So let's look at this carefully. Subtraction order matters. So once we go ahead and do the, it's asking us to calculate deviation from the mean, and for each of her commute. So let's go ahead and just do this deviation. So let's say, you see, this is the data right here. So one day it took her 45 minutes to bike to work, while her average is 44. So the deviation is going to be simply 45, take away 44. So we'll be subtracting 44 from each of those numbers. So here it takes her an extra minute. Here it takes her exactly the same as average, so 0. Now again an extra minute. Here it was 2 or 3 extra minutes. 43, note that, this one is the important one. 43 minus 44, that equals to -1, not +1. So that's actually took her faster. Then 2 minutes faster, 0 again, and then so on. So we got 3 minus 2, 41, that's -3, 43 minus 1, and 45 plus 1. Okay, so these are the numbers that we got. These are all the deviation. Let me give you a moment so you can compute the deviation for the subway ride, where the average is 43. Okay, so in a moment you're going to see all of this filled out for the subway. Here they are. Again, if you can print the lesson, then just copy the whole table the way you see it, because we'll need it in order to do our calculations for what we're trying to develop here. Okay, so you want to make sure you're writing those down. Okay, so these are the deviation for the subway and the bike. All right, so the minus indicates that it took her faster, right? While the plus means like plus 14 minutes from the average. That means it took her 14 minutes longer. All right, so the negative matters. All right, so let's see how this will be helpful as we learn about the measure of how the commute differs. So the deviation tells us how each value in a data set differs from the average. More variability in the data creates higher number for each deviation. Notice when we're computing the subway, the numbers that you see there when you subtract are bigger, right? That creates more variability. How do we measure that variability? So the question 4, is there a way we can calculate the variation for the data as a whole set? In other words, can we look at these numbers here, and can we look at those numbers there, right, and somehow define some kind of measure of variability as a whole data set? Let me give you a moment to think about it, and if you're not sure, then just say that, okay, because it's not clear what could be done. All right, so in this case, maybe you've said something about looking at these numbers and maybe summing them up, the ones that are highlighted. Maybe you were thinking about somehow averaging them out, or maybe taking absolute values, like removing the negatives and the positive, and just measure something that's called the absolute deviation. I mean, there are various ways, but in this lesson, we're actually going to define a real statistical measure that allow us to talk about that spread. Okay, so is there a way to calculate variation for the data set as a whole? Yes. And this is something that we're going to come up. All right, so if you wrote something great, we're going to start trying to do something about it. So question number 5. One of the approaches to calculate the total variation is to sum up all the deviation. So calculate the sum of everything that's highlighted yellow, just add them up. Minus means subtraction. If it's no minus, then you add it, put them together, and then get an answer, and then think about what did you get? Is that a useful information? I'll give you a moment. So add them up. What do you get? All right, so if you use your calculator and you add it, or with the highlighted yellow for the bike, it actually can be done, just in our head. 1 plus 1 is 2, then 5, then minus 1 is 4, then 2, then 5, then 3, then 0, then -1 plus 1, and then 0 again. So if you do it carefully, the sum is going to end up being 0 for both, for the subway and for the bike. It's just gonna add to 0. Now, so the sum will be 0. Sum of all deviations from the mean ends up being 0, which is should happen all the time. The reason why it's becoming 0, because that number, let's say for the bike, we got, what is it? Average was 44, right? 44 is like a scale, like a, what is it called? A balancing beam that where whether you go left or right, it's kind of level itself out. And all of these numbers that are to the left or to the right, for example, if you have 2 building blocks 1 unit away, here and here, and then you have 1 building block 2 units away, okay, then the scale will be equal, like it's going to be still equal at 44. So mean represents kind of a balancing point, so it will be 0 all the time for any data set. Now, question is, the fact that we're getting 0, is this useful? Does it tell us how the data are spread? Not really, okay? It just tells us that we calculated average correctly. That's it. That's why it becomes 0, but it doesn't tell us more. It doesn't tell us how numbers actually deviate, how the commuting time deviate. And that's where we will define a very important and very common measure in statistics that's called standard deviation, which is the title of today's class, or the main topic of today's class, which is this measure of spread. All right, so I'm giving you the steps here of how to calculate the standard deviation. All right, so we're going to first go ahead and, we come back to the data that we have, and let's copy all of the deviations for the bike. So we're just going to copy that numbers again. All right, here I copied the numbers. And now let's go very carefully. Let's understand how the calculation goes. So the next step is very crucial. We're going to take and we're going to, not this one. The sum is not important. The sum is going to be 0. So this is always going to be 0. This is the step that's important. We're going to, here. I apologize. I just looked right away to the second bullet point, assuming that the first one was not what I thought it was. So the first part, A, we're going, and these steps are very, very concrete. All right. So once again, understand where these numbers are coming from. All right. What are you doing? I don't want you to get lost all the way from the beginning. Remember, the average for the bike, which is the most important number that you need in order to start your computation, was 44. That was the average compute, minutes. So all of these numbers that are in purple are deviations, okay? You're just subtracting 44. We did it earlier, okay? Don't get lost here, because we want to make sure we understand where those numbers are coming from. The second step is we're going to take each of those purple numbers and we're going to multiply them by themselves, or we're going to square them. That's the square operation. I'm going to multiply it by themselves, and any number when you multiply by themselves is going to end up become positive. So all the negatives are going to drop out. So 1 squared is 1, then 0, then 1. Check this one out. This one is 9, then 1, then 4, 0, 9, 4, 9, 1, and 1. And this is the sum, so we don't need it. Okay? So those are what we call square deviations, okay? And the next step is what we're going to do. We're going to sum up all of these square deviations. So we're going to add all of these red numbers. Okay, so we're going to add them up. Okay, and let's see what we get. Did I write this out somewhere? No. Okay, so let's compute. All right, so if you add them all together, you will get 40. You get 40. As the sum of the square deviation. All right, so that's 40. And I'll look to this. The notation that we use for this, for the sum, is this. It's a Greek letter, capital letter, sigma. Sigma stands for the sum. And the way we write this is like this. This is called sum of square deviations. And that equals to 40. Okay. Then you're going to take that number that you get, 40, and you're going to average them out kind of over the course of all the numbers in the data set. How many numbers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you get 12 numbers. So n is 12, but you're not going to dividing it by 12. You're going to be dividing it by number of data points minus 1. That -1 is a statistical result. We don't go into as why that's the case, but that is to make our computation more reliable measure of the spread. So instead of dividing it by 12, you're going to divide always by a number less by one number than the total number of data points. So it's going to become square root 40 divided by 12 minus 1, which is 11. And at that point, you're going to go ahead and you will use your calculator. Okay, so 40 divided by 11 equals to 3.63. Keep this in your calculator and then take a square root. So take a square root of that answer. Square root is opposite of squaring, so it's going to be about 1.91, and the units are the same as the units of the regular data set. Alrighty, so we computed the standard deviation. So let's try to understand what that means. So the way we can write this in a sentence, we're going to say that Melissa's commute by bike takes on average how long? 44 minutes with standard deviation of about 1.91 minutes. Now, it would be a good idea to say it in other way, because when you say standard deviation, it sounds strange. What that means, what is 1.9 close to? It's about 2 minutes, correct? So informally, we say it takes her 44 minutes, give or take 2 minutes. So that gives us the variability. So let's say you biking, right? You know your data set. You calculated the standard deviation of 2 minutes. That means on a normal day, on a regular day, you wouldn't expect your commute to take more or less than 2 minutes away from 44. That means on a normal day, it's going to be what? 44 minus 2, which is 42 minutes, and 44 plus 2, which is 46 minutes. So that means this is going to be your aim. And then majority of the time, your commute is not going to be outside that range. You see how that standard deviation is kind of important? It gives us a ballpark of what to expect. All right. Now, what I would like for you to do on a separate piece of paper, go ahead and calculate the standard deviation for Melissa's commute on a subway so we can compare. All right. Take some time to do so. I recommend using this chart that we have right here. You see, because you already have all of the all of the deviation computed. So you need to square all these deviations, and then on a form, I'll ask you the following. I'll ask you to tell me what this is, sum of all the squares deviations. I'm going to ask you to tell me what n is, and finally, I'll ask you to compute this. What is it? Square root, not square root, the sum of all the square deviations. You will divide it by n minus 1, and then you will take the square root, okay? So I'll give you a moment to compute that, and then we'll review. Alrighty, so notice here are the numbers for all of the square deviations. Let me highlight it green for you right here. So all those numbers are much bigger than the one for the bike, right? So when you square all those numbers, notice they're all positive. then you take your calculator and you add them up, guys. You're going to get the sum of all of these is going to end up being 524. That's the total of all the squared deviations. Now, if you wonder why you square them, that's basically to remove the minus sign. Because if you have the minus sign, that means that everything is just going to sum up to 0. Having a squared gives us kind of like the deviation, positive deviation. And at the end, you take a square root just because you want to unsquare it back into the same units, which is the units, in this case, of time in minutes. So 12 is still there, right? It's still 12 numbers. And then you put this in a fraction mode. So you got 524 over 12 minus 1. I'm going to put 11 right away. Okay? So put 11 right away. Now, I just want to put this in the calculator for you because I know some students having trouble with just with correct substitution in the calculator. You can go ahead and use decimal scientific calculator. I really like it because it allows to put things nicely. So I can put the square root. I can also use a fraction, and I can nicely put my numbers in here, and it will give me the result. So it's 6.9 minutes. All right. So that is 6.9 minutes. Let's put it where it belongs, the answer. So I think it was question number 7, right? So for question number 7, we got the answer of square root of 524 divided by 11, which is 6.9. The usual notation for standard deviation is the letter S or sometimes SD. So in our class, we're not going to worry about the notation, so you can use whatever. You can use S for standard deviation. All right, in your word, describe the meaning of a standard deviation. I'll give you a moment. All right, so the standard deviation measures the average. It's a measure of average distance from the mean. All right, so it tells us where are the data located relative to the mean, to the arithmetic average. All right, and I'll write a paragraph, or you can write maybe 2 sentences comparing the variability in Melissa commute to work from home depending on the mode of transportation. So I'll give you a moment. So here the average time to commute by bike or train or subway are, I would say is, the average is comparable, meaning 44 and 43 minutes. However, the variability, commute by bike is more consistent, is more reliable and consistent. And consistent due to lower standard deviation. Standard deviation. Alrighty. Okay, so this is the measure that we introduced, the standard deviation, which is measure the distance from the mean. So we understand hopefully how to compute it, and on My Open Math you get some opportunity to practice computing the standard deviation. Now let's conceptually go over a few examples, and not that many here, just telling us the importance of standard deviation in different situations. So let's read of each of the scenarios where the standard deviation was computed for us. And for each case, decide whether the standard deviation is significant to the claim made about the data and explain your conclusion. So is the standard deviation important in describing whatever is being stated? So question number 1, a new supplement claims to dramatically promote weight loss. Its manufacturer It manufacturer cites a study where 15 participants have an average weight loss of 10 pounds with a standard deviation of 8 pounds over the course of the 1 month. So is standard deviation significant to this claim? What does it tell us? Is it an important measure? Yes or no? All right, so let's review. Yes, it definitely significant. All right, if the standard deviation is 8, that means that a person could potentially lose as high as, what is it? So standard deviation is 8 and the average loss is 10. So we can have somebody who lose as high as 18 pounds, or you can lose as few as only 2 pounds. So there's a big variability range. So when you hear that the standard deviation is 8, you should be a little bit skeptical about that claim, because then, you know, one can lose 18, but somebody can lose as little as 2. So then that gives us a better picture of what's actually happening. All right, so it gives us a broader range. 2, a local district in New York City claims that the 8th grade math scores improved from the year before. Below is the data reported. So 2016, the average was 65. And the standard deviation was 10. The following year, the average improved, but the standard deviation decreased. So what can you say about how does the year 2016 compare to 2017? I'll give you a moment to think about it. Did it actually improve? Well, to answer this question, what I like to do is always subtract the standard deviation and add a standard deviation, just to see where the majority of folks scored. So 65 minus 10 is 55, and 65 plus 10 is 75. So that means that the range is between 55 and 75. That's what we see. And we're talking about the average scores. Okay, so that means the average scores are of all the students are going, all the students scored anywhere between 55 and 75 on that math assessment or whatever it is. All right, now while on the other year it becomes 68 minus 8, so the scores are between 60% and 76%. Okay, so, 60, right? 60 and 76. Yeah, I said the right thing. It just looks like this is not a 0. So it's between 60 and 76. Now, how would you compare this? Well, the lower end of the scores did improve, but the higher end of the scores is kind of still, you know, in a 76 range. So it is improved slightly, but the lowest standard deviation tells us that it's not as spread out. Okay, so the scores are a little bit more consistent. Okay, so it's also important in sort of understanding what the data telling us. How about the next one? Official in Punta Cana, Dominican Republic, claim that the city has consistently warm weather year-round, which makes it perfect destination for people to visit. All right. Table below lists average temperature for each month of the year. Average and a standard deviation is also listed. So we got the temperatures, all right, and the standard deviation here is 2. So does the standard deviation tell us that the temperature in Dominican Republic in Punta Cana consistent a year round? What do you think? Definitely, the standard deviation equals to 2 shows consistency. Meaning that the temperature doesn't vary as much. You see, there's not much variability. Just like our bike Commute, a small standard deviation demonstrates consistency. Keep that in mind. That's a quantitative reasoning sort of understanding of a standard deviation. The smaller it is, the more consistent it is. All right. So the temperature in Punta Cana is really nice and it's really consistent year around. And finally, this is a little outdated statistics for Stephen Curry, telling what was his points per game statistics on average. So in the 2014-2015 season, he played most of the games here, and he scored on average the highest number of points per game out of all the other stars in that year. All right, so the highest number. However, his standard deviation was the most highest. So is he consistent compared to others based on that? And I'll give you a moment to write a sentence. You don't have to write an essay about what you feel, and give me all of your knowledge about the game, but just for the sake of mathematics, looking at the standard deviation, what does standard deviation tell us? Well, let's review. According to this data, he has the highest standard deviation. So again, that might sound a little, maybe you might start arguing about this, but according to this data, he is the least consistent player in that season because of the largest standard deviation. He is still the top scorer, but that number creates a wider range, meaning that in some games he can score as low as 20, while in some other games he scored as high as 40. All right, so in the next lesson will be more quantitative when it comes to describing the notion of the standard deviation. So we'll be able to attach probability to what we're talking about. But this is our last question in that lesson. So on that, we'll finish.